So, Nvidia CEO Jensen Huang delivered an amazing presentation at this year's CES in Las Vegas. In this video, we're going to cover everything he talked about, including the new GPUs, their new World Foundation models, and plenty more. But what I really wanted to focus on, and what I think is really the most important thing from this entire conference, is their plans for general robotics. As Jensen himself says,
the ChatGPT moment for general robotics is just around the corner.
So to start off, they show us a graph depicting the progression of AI in multiple stages. In 2012, we have the creation of AlexNet, a convolutional neural network architecture designed by Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton. This was kind of the moment that really kicked off deep learning. Then we have perception AI, AI that can understand speech, text, and images, followed by generative AI, AI that can generate speech, text, and images. This would be ChatGPT and LLMs in general. The next stage or level of AI is going to be agentic AI. So they list coding assistants, customer service agents, patient care, and I mean, that's really only scratching the surface. I'd say we are pretty much at the very beginning of the agentic AI stage. This year and the following few years to come is when we will truly start to see the impact of AI agents. But where Nvidia sees AI going next, since we're basically in the agentic AI stage right now, is physical AI. That is self-driving cars, general robotics, pretty much just embodied AI. As we'll see later in the video, they are making incredible strides in this area, and they're doing it in a way that you might not have expected. Before we get into all of that though, there is this slide here where they talk about the 3 scaling laws. First, we have pre-training scaling, which is essentially scaling up the data that we train these models on. So the larger a model is, the more parameters it is, the better it performs. This is the main scaling law that took us all the way from GPT-2 to GPT-4o. The issue with scaling pre-training though is there is only so much data, and AI companies have pretty much already exhausted all the available data. Jensen does point out that there's a ton of new data being generated every single day, but the point is there are still hard constraints. Now, the second scaling law relates to post-training scaling, which includes techniques like reinforcement learning, prompt engineering, fine-tuning, and so on. This is where the model actually learns and improves. After training it on a large dataset during pre-training, you then provide feedback on its outputs to refine its skills and make it more accurate during post-training. And finally, the third scaling law, which is a relatively new scaling law, is test time scaling or reasoning. This new scaling paradigm is what birthed OpenAI's new O model series, like O1 and O3, and here is a short clip of Nvidia CEO explaining it better than I ever could.
We now have a third scaling law, and this third scaling law has to do with what's called test time scaling. Test time scaling is basically when you're being used. When you're using the AI has the ability to now apply a different resource allocation. Instead of improving its parameters, now it's focused on deciding how much computation to use to produce the answers it wants to produce. Reasoning is a way of thinking about this. Long thinking is a way to think about this. Instead of a direct inference or one-shot answer, you might reason about it. You might break down the problem into multiple steps. You might generate multiple ideas and evaluate, your AI system would evaluate which one of the ideas that you generated was the best one. Maybe it solves the problem step by step, so on and so forth. And so now test time scaling has proven to be incredibly effective.
Now let's talk about some of the products they have coming up, starting with their next generation of GPUs, the RTX Blackwell 50 series. So these not only deliver a massive performance increase, but they are also somehow cheaper. As you can see, the RTX 5070 is retailing at $549 and offers the same performance as the previous state-of-the-art RTX 4090. Along with the 5070, they have a few other models including the RTX 5090, which is retailing at $2,000. These will become available starting in January. Now, to give you a sense of the kind of performance you can get from these, here is a video game being rendered on the new RTX 5090. What's so crazy about this is that these new GPUs use neural nets to generate roughly 90% of the pixels, meaning the majority of the graphics are AI. Traditional ray tracing algorithms only render about 10%, kind of like a rough sketch, and then a generative model fills in the rest of the fine details in one forward pass in real time. So this is literally a video game being generated in real time by AI, and as you can see, the graphics are extremely high quality. At this rate, I think it's pretty clear that we will start to see a lot of video games being rendered this way using primarily AI because it's simply a lot more efficient and the performance continues to increase rapidly. Nvidia also showed off their new AI chip for cloud providers called the Grace Blackwell NVLink 72.
Here we go. Sorry, guys. You see that? That's cool. Look at that. Disco lights in here.
This is essentially a massive AI chip. As you can see, it comprises of 72 Blackwell GPUs and has 14 terabytes of memory.
It has 14 terabytes of memory, but here's the amazing thing. The memory bandwidth is 1.2 petabytes per second. That's basically the entire internet traffic that's happening right now. The entire world's internet traffic is being processed across these chips, okay? And we have 130 trillion transistors in total, 2,592 CPU cores, whole bunch of networking.
These are just some absolutely mind-boggling numbers. It's hard to believe that something like this is even possible. I can't imagine what it costs. My guess would be probably somewhere in the millions, but let me know in the comments, how much do you guys think this thing costs? Moving on, there was one more product Nvidia unveiled at this conference, and that is their consumer-based mini AI supercomputer.
But now artificial intelligence is everywhere. It's not just in researchers and startup labs. You know, we want artificial intelligence, as I mentioned in the beginning of our talk. This is now the new way of doing computing. This is the new way of doing software. Every software engineer, every creative artist, everybody who uses computers today as a tool will need an AI supercomputer. And so I just wish that DGX-1 was smaller. And imagine, ladies and gentlemen, this is NVIDIA's latest AI supercomputer.
So this is a cloud computing platform that sits on your desk. You can connect it with your PC or your Mac or pretty much any computer, and it essentially allows you to tap into the immense power of a supercomputer from your personal computer. You can also stack them and double your performance. Now, this is where it starts to get really crazy. If you thought what we saw already was pretty cool, I mean, it was, but this next part where they talk about physical AI is absolutely mind-blowing. This clip I'm about to show you is a bit long, but trust me, you're gonna want to pay attention because he's literally describing the future of AI.
So, physical AI. Imagine, whereas your large language model, you give it your context, your prompt on the left, and it generates tokens one at a time to produce the output. That's basically how it works. The amazing thing is this model in the middle is quite large, has billions of parameters. The context length is incredibly large because you might decide to load in a PDF. In my case, I might load in several PDFs before I ask it a question. Those PDFs are turned into tokens. The basic attention characteristic of a transformer has every single token find its relationship and relevance against every other token. So you could have hundreds of thousands of tokens, and the computational load increases quadratically. And it does this, all of the parameters, all of the input sequence, process it through every single layer of the transformer, and it produces one token. That's the reason why we needed Blackwell. And then the next token is produced when the current token is done. It puts the current token into the input sequence and takes that whole thing and generates the next token. It does it one at a time. This is the transformer model. It's the reason why it is so incredibly effective. Computationally demanding. What if instead of PDFs, it's your surrounding? And what if instead of the prompt, a question, it's a request? Go over there and pick up that box and bring it back. And instead of what is produced in tokens as text, it produces action tokens. Well, that I just described is a very sensible thing for the future of robotics. And the technology is right around the corner. But what we need to do is we need to create the effectively the world model of, as opposed to GPT, which is a language model. And this world model has to understand the language of the world. It has to understand physical dynamics, things like gravity and friction and inertia. It has to understand geometric and spatial relationships. It has to understand cause and effect. If you drop something, it falls to the ground. If you poke at it, it tips over. It has to understand object permanence. If you roll a ball over the kitchen counter, when it goes off the other side, the ball didn't leave into another quantum universe. That's still there. And so all of these types of understanding is intuitive understanding that we know that most models today have a very hard time with. And so we would like to create we need a world foundation model. Today we're announcing a very big thing. We're announcing NVIDIA Cosmos, a world foundation model that is designed, that was created to understand the physical world. And the only way for you to really understand this is to see it. Let's play it.
Now, before we take a look at this clip that he just set up so amazingly, I wanted to quickly reiterate what he just said. So just like how we have LLMs, which are large language models that essentially understand and mimic human language, the next thing we will have is WFMs, or World Foundation Models. These are models that understand the real world. While LLMs output text and image tokens, WLMs output action tokens. So you can ask ChatGPT, for example, to write you a story, but you can't ask it to go to the fridge and get you a beer. With a WLM, though, that is embedded in a humanoid robot, you can. As Jensen also said, the only way to explain it would be to show you, so here's the clip.
Bringing the power of foresight and multiverse simulation to AI models, generating every possible future to help the model select the right path. Working with the world's developer ecosystem, Nvidia is helping advance the next wave of physical AI.
So can we just take a moment to appreciate how insane this is? Like, this is literally a model that generates simulations of the world. The simulation hypothesis, the idea that our reality is a simulated reality, is looking a lot more probable. I mean, if you think about the eventual progression of all this, the simulations will continue to get better and more realistic, and we will likely get to a point where we can create simulations of the entire world. Obviously, this is still a ways away, but it makes you wonder, is this actually the first time objectively that world simulations have been created, or are we just replaying the course of of history inside of a simulation, completely unaware of what's actually going on. Now, thinking more short term, there are a ton of reasons why WFMs will be extremely useful. You can use them to train humanoid robots, gathering synthetic data in a simulation much faster than you could in the real world. You can use them to train autonomous vehicles, as we'll see more of later, and companies can also use them to create digital twins of their warehouse, for example, as we're seeing in this clip, to simulate multiple processes or scenarios to find the most efficient way of doing things without actually ever testing it in the real world. This extends to not only warehouses, but pretty much anything. Finally, the last area Jensen touches on is general robotics, and specifically self-driving cars. Personally, self-driving cars is something that I am really interested in. I think inevitably they are going to take over, and it will be one of the biggest industries we have ever seen. Self-driving cars have the potential to drastically reduce the dangers of transportation, while simultaneously making it cheaper and more efficient. I mean, who wouldn't want that? I mean, I could think of a few people who probably wouldn't want that, like taxi drivers, Uber drivers, truck drivers, etc., but at the end of the day, it is coming. So they talk about how Nvidia is partnered with pretty much every major car company right now, and how this industry is likely going to be the first multi-trillion-dollar robotics industry. But what's truly fascinating is how Nvidia is using synthetic data generated by Cosmos and Omniverse, as we just saw, to actually train these autonomous vehicles. Take a look.
Okay, so now I told you I was going to show you what would we use Omniverse and Cosmos to do in the context of self-driving cars. And today, instead of showing you a whole bunch of videos of cars driving on the road, I'll show you some of that too. But I want to show you how we use the car to reconstruct digital twins automatically using AI and use that capability to train future AI models. Okay, let's play it.
The autonomous vehicle revolution is here. Building autonomous vehicles, like all robots, requires 3 computers: Nvidia DGX to train AI models, Omniverse to test drive and generate synthetic data, and Drive AGX, a supercomputer in the car. Building safe autonomous vehicles means addressing edge scenarios, but real-world data is limited, so synthetic data is essential for training. The Autonomous Vehicle Data Factory, powered by Nvidia Omniverse, AI models, and Cosmos, generates synthetic driving scenarios that enhance training data by orders of magnitude. First, OmniMap fuses map and geospatial data to construct drivable 3D environments. Driving scenario variations can be generated from replayed drive logs or AI traffic generators. Next, a neural reconstruction engine uses autonomous vehicle sensor logs to create high-fidelity 4D simulation environments. It replays previous drives in 3D and generates scenario variations to amplify training data. Finally, Edify 3DS automatically searches through existing asset libraries or generates new assets to create sim-ready scenes. The Omniverse scenarios are used to condition Cosmos to generate massive amounts of photorealistic data, reducing the sim-to-real gap. And with text prompts, generate near infinite variations of the driving scenario. With Cosmos Nemotron Video Search, the massively scaled synthetic dataset, combined with recorded drives, can be curated to train models. Nvidia's AI Data Factory scales hundreds of drives into billions of effective miles, setting the standard for safe and advanced autonomous driving.
So the self-driving cars will literally all be like expert human drivers. In fact, even better than expert human drivers, as they will be trained on multiple lifetimes of driving scenarios. Now, before we end the video, I wanted to show you guys this brief clip where Jensen recaps the 3 major areas of robotics that Nvidia is targeting. These are the 3 major areas of robotics that have the most potential and are likely the type of robots we will be seeing very soon.
There are 3 robots in the world that we can make that require no green fields. Brownfield adaptation is perfect. If we could possibly build these amazing robots, we could deploy them in exactly the world that we've built for ourselves. These 3 robots are, 1, agentic robots, and agentic AI. because, they're information workers. So long as they could accommodate the computers that we have in our offices, it's going to be great. Number 2, self-driving cars. And the reason for that is we spent 100 plus years building roads and cities. And then number 3, humanoid robots. If we have the technology to solve these 3, this will be the largest technology industry the world's ever seen. And so we think that the robotics era is just around the corner.
So overall, a fascinating presentation here from Nvidia. I hope you guys enjoyed that recap. As always, thank you guys for watching, and don't forget to check out my Patreon. I actually just started it up. I will be posting weekly and monthly AI news recaps there, as well as exclusive model tests and more. It's also just a great place to chat with other members of the community or myself. I've already been talking with a few of you in there, so definitely check it out if you're interested. The link is in the description, as well as my channel bio. Anyways, that's all for today. Again, thank you guys so much for watching, and if you want to stay up to date on future AI news just like this, make sure to hit that subscribe button.